Right, so now what I want to do is record a general formula for changing variables called the change of variable formula for densities. We actually already saw special case of this in the previous lecture where we talked about how we could compute the density of a transformation when the transformation was strictly increasing continuously differentiable function. And so more generally speaking, the change of variables formula says that if we suppose G is monotone and differentiable, so monotone means it's either increasing or it's decreasing. And X is continuous random variable with density F sub X, then the transformation G of X has density Fy, which is the density of X evaluated at H of Y times the absolute value of H of Y. This is where, again, we've defined H of Y as the inverse of G. The inverse of G exists because, again, G is assumed to be monotone, so it's either strictly increasing or strictly decreasing. The biggest difference here, we see we pretty much have the same thing up here. The biggest difference is in this absolute value. So when H is an increasing, or when G is an increasing function, its derivative will be positive, and so the absolute value is just the derivative. When G is decreasing, the derivative will be negative, and so this absolute value is necessary to make this be a density. Let's work out a couple of examples of see how we can apply this. Okay, first example is we're going to let X have a density. Let's see. Let me label this. This is what's called a location scale transformation. So X is going to have a density F sub X, and Y is going to be defined as the transformation AX plus B for constants A and B, and A not equal to 0. If A is 0, then we're multiplying X by 0. We're just getting a constant back. Okay. So then in this case, in terms of the above change of variables formula, G is AX plus B. H of Y, which is G inverse, is Y minus B divided by A. Okay. And the derivative of H is 1 over A. So then that's what we need to determine that Y in this case has a density that can be computed from the density of X And the density is f of x evaluated at h of y. So f of x evaluated at y minus b over a times 1 over the absolute value of a. Okay. So this is, in general, the distribution or the density of a location scale family. We can define a location scale family for any random variable by taking a random variable and letting a and b vary and getting the family of densities that we define here. Okay. So as a special case, suppose we have a gamma random variable, gamma R1, and we define y as x divided by lambda. Well, we had this as an exercise before. So what is f of x? Right? Well, it's x to the r minus 1, 1 to the r, which doesn't do anything, e to the minus x over gamma function of r. This is for values of x bigger than 0. So then what's the value of, so in this particular case, g of x equals x over lambda. So a is 1 over lambda, and b is 0. Okay. So what we're left with then is lambda times fx evaluated at lambda y. So we get lambda y to the r minus 1, e to the minus lambda y over gamma r times lambda. Well, lambda was assumed to be bigger than 0. So what we're left with then is lambda to the r y to the r minus 1, e to the minus lambda y over gamma r, right? This, of course, is the density of the gamma with parameter r lambda. For another example, let's take U to be uniform, 0, 1, and let's define y as minus log of U. So first of all, I should have pointed out, is G, we had to check, we should have checked that G was a monotone increasing or decreasing function. And it is, because AX plus B is just a line, right? Is, in this case, G, right? First of all, we note that U and Y, in this case, are both positive, well, non-negative, because U is between 0 and 1. We're taking the log of something between 0 and 1. That's a negative number. So log is defined for positive real numbers. Above 1, the log is, that's what the log looks like. So this is 1. The log looks something like this. Okay, this is log. Okay. So it's monotone increasing continuous differentiable. And that's our function g. And so we're taking the log of a uniform, which is between 0 and 1. So that's negative. And then we're taking the negative, so that flips it up to be positive. we have g of u defined as minus log of u, that's monotone. When we flip it around, h of y is e to the minus y, right? To undo the log, well, first we undo the negative, then we undo the log by taking exponential. And the derivative of hy is minus e to the minus y, okay? So then, putting it all together, what do we get? The distribution, the density of y is the density of u evaluated at g of u, which is minus log of u, times the absolute value of minus e to the minus y. So y has to be positive because u is between 0 and 1, forces y to be positive. So this is the density of u is 0 when u is greater than 1 or less than 0. Okay. And then anything else, it's going to be 1. So this is just 1 if minus log of u is positive. Okay, so let me put this here. So the density is 1 times e to the minus y if y is positive, 0 otherwise. So in other words, this transformation, which is the minus the log of a uniform, is standard exponential. So we can generate, we talked about how we can construct a uniform 0, 1 random variable. And this is a case where we see that if we construct a uniform 0, 1 random variable, we can actually manufacture a standard exponential random variable just by transforming the uniform. And that's something that in general we can do, and it's actually a very important property of random variables, as we'll see. Okay. Another example, let's let x be exponential with rate lambda, and let's define y to be the square root of x. Well, because x is exponential, it's non-negative. So the square root of x is defined, and the square root of x looks something like this. Continuously differentiable, right? So then in this case, g of x is a square root. H of y is y squared. H prime of y is 2y. And the density of y is fx h of y, absolute value of h prime of y. This is for y bigger than 0. Well, fx is lambda e to the minus lambda h of y, which is y squared, times the derivative, which is 2y. So it's 2, say lambda y e to the minus lambda y squared for y bigger than or equal to 0 and 0 otherwise. We saw this before, if you remember. This was the Raleigh distribution. So the Raleigh distribution in general, a Raleigh random variable with parameter lambda looks something like this. This was Raleigh, I'm sorry, Raleigh with parameter lambda. Here we have a 2 lambda. So this is standard Raleigh with parameter 2 lambda. So the Rayleigh distribution, which we saw before, we got it another way. Here we get it as the square root of an exponential. Okay, so those are a few examples how transformations can be very useful. The change of variables formula in particular can be extremely useful for deriving properties of random variables that we express in terms of other random variables.